Hi, I'm Alex. Even the fastest thing in the universe takes years just to reach the nearest stars. At that scale, crossing our galaxy isn't a journey for humans, it's a timeline for civilizations. But now, scientists are exploring a very different approach, not moving faster than light, but reshaping space itself to cross distances once thought impossible. Today, we're going to explore how this idea emerged. If journeys like this spark your curiosity, a gentle subscribe helps this channel keep growing. Now let's begin. A beam of light left Earth this morning, the fastest thing in the universe. It punched through the atmosphere in 0.004 seconds, circled the planet 7.5 times in a single heartbeat, fast enough that if you blinked, it would have already touched the moon and returned. Nothing moves quicker. Not rockets, not signals, not information itself, but to reach the nearest star 4 years and 2 months. This is not distance in the ordinary sense. This is cosmic isolation, a form of imprisonment built into the structure of reality itself. The universe is vast, not just in scale, but in a way that actively resists human intuition. Space does not merely separate us from other stars, it locks us away from them. Consider Voyager 1, launched in 1977. It is the fastest spacecraft humanity has ever built. It screams through the void at 61,000 kilometers per hour, 50 times faster than a bullet, fast enough to cross the United States in 10 minutes. A triumph of engineering, a monument to ambition. After 46 years of flight, it has only just left the solar system, the neighborhood, our front yard. That is all Voyager has managed in nearly half a century of continuous travel. To reach Alpha Centauri, the nearest star system beyond our own, it would need another 75,000 years. Not 75 years. 75,000. Let that settle for a moment. Imagine you are 30 years old. You have a 5-year-old child. You place that child on Voyager 1 and send them toward Alpha Centauri. Your child will not arrive. Their children will not arrive. Their grandchildren, great-grandchildren, descendants, stretching across 3,000 generations, will live and die aboard that vessel before anyone sees the destination. Generation 1 remembers Earth. They know the mission. They carry photographs, recordings, memories of blue skies and ocean waves. Generation 50 has only heard stories. Earth is a place their great-great-grandparents described distant and abstract. Generation 500 regards Earth as a myth, a legend passed down details blurred by time, half believed at best. Generation 2, wives and daughters, does not believe Earth ever existed. It has become religion, not history. Generation 3, Uranus and Norris, arrives at Alpha Centauri. They have forgotten why they are traveling. The mission has been lost to time, the purpose erased. They are simply people on a ship drifting through the void because that is all they have ever known. 75,000 years is not a journey. It is geological time. It is the span between species. The entire Egyptian civilization lasted 3,000 years, from the first pyramids to the final collapse. 75,000 years is 25 times that duration. The pyramids themselves, monuments built to defy eternity, have crumbled into sand. And this voyage would be 25 times longer than the entire arc, from pyramid construction to ruin. Even our second fastest spacecraft, New Horizons, took 9.5 years just to reach Pluto. And Pluto is still inside the solar system, still within our cosmic backyard. The actual stars remain unreachably distant, separated not by space alone, but by time so vast it erases meaning. The Egyptians built pyramids. and believed they would last forever. 3,000 years later, those pyramids are dust. Our spacecraft, it would become drifting debris long before completing even 1/25th of the journey to the nearest star. But this is only the beginning. The real problem is not that our ships are slow. The real problem is that physics forbids them from going faster. You want the ship to go faster, so you add fuel. But fuel has mass. Mass makes the ship heavier. A heavier ship needs more fuel. More fuel adds more mass, which requires even more fuel, which adds more mass. This is not a feedback loop. This is a mathematical trap with no exit. The equation that governs this nightmare is the Tsiolkovsky rocket equation. It is beautiful in its simplicity and brutal in its implications. Every aerospace engineer knows it. Every spacecraft designer is imprisoned by it. Here is what it demands. Take a 1-ton spacecraft, small, roughly the size of a car. You want it to reach 10% of light speed, not fast by cosmic standards. At that velocity, reaching the nearest star would still take 42 years. But 10% of light speed is already an extraordinary goal. The fuel required 3 million tons. 3 million tons of fuel to move 1 ton of spacecraft. A fuel-to-payload ratio of $3,000 to 1. For perspective, the Saturn V rocket that sent humans to the moon had a fuel-to-payload ratio of 50 to 1, and it only needed to cover a 3-day journey to our nearest celestial neighbor. Now imagine trying to reach 50% of light speed with that same 1-ton ship. The fuel requirement becomes an asteroid. Not metaphorically, literally an asteroid several kilometers in diameter, converted entirely into propellant. And even this assumes conventional fuel. What about antimatter? The most efficient propulsion system theoretically possible. Matter and antimatter annihilate on contact, converting 100% of their mass into energy. No waste. Perfect efficiency. The absolute ceiling of what physics allows. Even with antimatter, a 10-ton spacecraft would require 400,000 tons of fuel to reach relativistic speeds. Humanity currently produces a few nanograms of antimatter per year. At that rate, gathering enough fuel would take longer than the age of the universe. Between 1996 and 2002, NASA ran the Breakthrough Propulsion Physics Project. The mission was simple: find any plausible method to send a spacecraft to another star. 6 years of research, hundreds of scientists, every promising idea explored, tested, and analyzed. Their conclusion: to reach the nearest star within a human lifetime would require energy equivalent to the mass of 1,000 Earths. The final report used 2 words: fundamentally impossible. Not difficult, not impractical. Impossible. With conventional propulsion, the energy requirements do not merely exceed our capabilities. They exceed anything imaginable. You cannot brute force your way across interstellar space by burning fuel and throwing mass backward. The numbers do not allow it. It is like trying to swim across the Pacific Ocean, except the water has the consistency of concrete, and the faster you swim, the thicker it becomes. Eventually, movement itself becomes impossible. This is the point where serious scientists gave up, where the equations closed every door and locked every exit. Faster than light travel was not merely beyond our technology, it was beyond physics itself. But this story does not end here, because there was one person who had not yet given up. Before the ship could even accelerate, the universe had already erected the final barrier, a barrier written into reality by a genius 120 years ago. And that barrier was absolute. 1905, a 26-year-old man sat in a Swiss patent office. No laboratory, no spacecraft, no telescope, just a pen paper and a mind capable of seeing what no one else could. He wrote the most beautiful equation of the 20th century, E, MC2. Hidden within that equation was a death sentence for every spacecraft ever conceived. No object with mass can exceed the speed of light. Not difficult, not impractical, forbidden. Why? Because as a ship accelerates, its mass increases, not metaphorically, literally. The faster it moves, the heavier it becomes. And this is not speculation. It is measured fact confirmed every single day inside the Large Hadron Collider. Take a proton. At rest, its mass equals 1. Accelerate it to 99.9% of light speed. Its mass becomes 22 times greater. At 99.99% of light speed, the mass increases to 70 times the original. At 99.9999%, the proton weighs 707 times what it did at rest. At 99.9999% of light speed, a single proton weighs as much as a mosquito. One subatomic particle becomes as heavy as an insect simply by moving fast enough. The LHC proves this thousands of times per second. The measurements are precise. The effect is real. Now apply this to a spacecraft, a 100-ton ship traveling at 99.9% of light speed suddenly weighs 2,200 tons. The engines must push harder, but heavier engines add mass, which increases the total weight, which demands even more power. The closer you approach light speed, the worse the problem becomes. At 99.99%, the ship weighs 7,000 tons. The engines are now pushing against a mass 70 times greater than what they started with, and they themselves contribute to that mass. To reach 100% light speed, the energy required becomes infinite. Not very large, not unimaginably vast. Infinite, undefined, the mathematical equivalent of dividing by 0. The equation breaks. The universe returns an error. You cannot reach light speed by accelerating through space, because mass resists acceleration, and the faster you go, the more mass you gain, and the more energy you need, and the cycle has no resolution. Physics does not bend on this point, but there is a second consequence, equally devastating. Time itself stops cooperating. A ship traveling near light speed experiences time more slowly than the rest of the universe. This is not a minor effect. It is dramatic, measurable, and unavoidable. Imagine this scenario. You are 25 years old. You board a spacecraft capable of reaching 99.99% of light speed. Your destination is a star 50 light years away. The journey from your perspective aboard the ship takes 8 months. You arrive, conduct your mission, and return. 8 months out, 8 months back. You have aged 16 months total. But on Earth, 100 years have passed. Your parents died 70 years ago. Your friends, if they survived, are now 95 years old. You step off the ship at 26, and the world you left behind has aged a century. Children you never had have grandchildren older than you. You are a living ghost, temporally displaced, separated from everyone you knew not by space but by time. This is not science fiction. Atomic clocks, flown on jet aircraft around the Earth, run slower than clocks on the ground by a few nanoseconds, exactly as Einstein predicted. The effect scales with velocity. Near light speed, it becomes catastrophic. You wave goodbye to your 5-year-old daughter. You return and she died last year, at 105. Welcome home. For 50 years, every serious scientist accepted this as the end of the discussion. Physics had spoken. Faster than light travel was impossible, and even approaching light speed carried consequences no human society could accept. But then someone noticed the loophole. Einstein forbade ships from moving faster than light. But did he forbid space itself from moving? The answer is no. And that gap, that narrow, overlooked detail changes everything. Right now, at this very moment, millions of galaxies are receding from us faster than light, not because they are flying through space at impossible speeds, because the space between us and them is expanding. The galaxies themselves are nearly stationary. Space carries them. This does not violate relativity. Nothing locally exceeds light speed. Space itself is doing the moving, and Einstein's equations place no limit on how fast space can stretch, compress, or flow. Visualize it this way. Draw two ships on the surface of a balloon. Inflate the balloon. The ships move apart, but neither one has fired its engines. The balloon expands. Space expands. The ships are simply along for the ride. This is not theoretical. It is observable fact. During the first fraction of a second after the Big Bang, space expanded faster than light by a factor of 10 to the 26th power. The universe grew from smaller than an atom to larger than a galaxy in 0.1 seconds. No object moved. Space itself inflated. Even now, the most distant observable galaxy, GNZ 11, is receding from us at 2.3 times the speed of light. Completely legal. No violation. The galaxy is not traveling through space faster than light. The space between us is expanding. Einstein's law prohibits objects from moving through space faster than light. It says nothing about space carrying objects along. This distinction sounds trivial. It is not. Here is the breakthrough idea. Instead of accelerating the ship warp, the space around it, contract space in front, expand space behind. The ship remains stationary within its local bubble of spacetime, while spacetime itself moves. Like standing on an airport, moving walkway. You are not running, but you move quickly relative to the terminal. The walkway does the traveling. You stay still. Traffic law prohibits driving faster than 100 kilometers per hour, but it does not prohibit sitting motionless on a bus traveling 100 kilometers per hour, driven by someone else. The spacecraft engineers had been solving the wrong problem. They did not need a faster ship. They needed space itself to move. The universe has a speed limit, but the limit applies to motion through space, not motion of space. And if space can move freely, then anything embedded within it can travel arbitrarily fast without ever locally exceeding light speed. For decades, physicists tried to make ships go faster. They built bigger engines, searched for better fuel-optimized trajectories. All of it was futile, because they were fighting space-time directly. The real question was never how to outrun physics. It was whether physics could be redirected, whether space-time flexible and dynamic could be shaped deliberately rather than passively endured. And to answer that question required understanding something even stranger. Gravity does not exist. You're sitting in a spacecraft with no windows. The ship accelerates upward at 9.8 meters per second, squared exactly equal to Earth's gravity. You feel pressed into your seat. The sensation is indistinguishable from sitting in a chair on the ground. There is no experiment you can perform, no measurement you can take that will tell you whether you are accelerating through space or sitting stationary in a gravitational field. Einstein realized this in 1907. Gravity and acceleration are identical, not similar, not analogous, the same. In 1915, he published General Relativity and revealed the deeper truth. Gravity does not exist. There is no force pulling objects together. There is only space-time curved by mass and objects following the straightest possible paths through that curvature. Imagine a flat rubber sheet that represents flat, empty space-time. Place a bowling ball in the center. The sheet sags. Now roll a marble across it. The marble curves toward the bowling ball, not because any force pulls it, but because the shape of the surface has changed. The marble is simply following the geometry. That is gravity, not a force, a curvature of space-time itself. We have proof. GPS satellites orbit at 20,000 kilometers altitude, where space-time is less curved by Earth's mass. Clocks on those satellites run 38 microseconds faster per day than clocks on the ground. If engineers did not account for this effect, GPS would be off by 10 kilometers after a single day. Every spacecraft, every satellite must correct for space-time curvature, not because of some theoretical abstraction, but because ignoring it causes measurable, catastrophic errors. In 2015, LIGO detected gravitational waves, ripples in space-time itself, produced by two black holes colliding 1.3 billion light-years away. The distortion measured was smaller than 1/10,000th the diameter of a proton, yet it was detected. Space-time is not a rigid stage. It is a dynamic fabric that bends, stretches, and ripples. If space-time can ripple, it can be curved. And if it can be curved, perhaps it can be controlled. This realization transforms spacecraft design. Space-time is not a passive backdrop. It is an active participant. Mass curves it automatically. The sun bends space-time. Earth bends space-time. Every object with mass reshapes the geometry around it. The question becomes, can a spacecraft learn to bend space-time deliberately without needing the mass of a star, without relying on natural gravitational fields? Just with the right technology applied in the right way, the speed limit remains absolute for objects moving through space. But if space-time itself can be engineered shape, directed, then motion stops being about velocity and starts being about geometry. And in 1994, a man named Miguel Alcubierre did the impossible. He wrote the first design for a ship that could travel faster than light, completely legal, under the laws of physics. 1994. Miguel Alcubierre was 28 years old, a graduate student working through Einstein's field equations. He was not trying to build a starship. He was exploring mathematics, searching for solutions that had been overlooked. What he discovered was a configuration that should not have been possible, yet the equations permitted it. Einstein's equations allowed a ship to remain stationary while space itself moved. The design was elegant and disturbing. Alcubierre described a bubble of warped space-time surrounding the vessel. In front of the ship, space contracts. Behind the ship, space expands. Inside the bubble, space-time remains completely flat. Time flows normally. Physics behaves exactly as it does on Earth. But the bubble as a whole can move, and it can move at any speed. 10 times light speed, 100 times, 1,000 times. The equations place no limit. Locally, nothing exceeds light speed. The ship itself is motionless within its bubble. But relative to distant observers, the bubble crosses vast distances in impossibly short time. It is like standing on an airport, moving walkway. You are stationary relative to the walkway surface, but you travel quickly relative to the terminal because the walkway itself is moving. The ship does not accelerate. Space does the traveling. This solved every problem simultaneously. No infinite energy requirement because the ship never approaches light speed locally. No time dilation because the crew experiences flat spacetime inside the bubble. No crushing acceleration forces because nothing accelerates. The universe reorganizes itself around the vessel while the vessel remains at rest. On paper, it was flawless. The Large Hadron Collider proves daily that objects cannot exceed light speed through space. Protons accelerated to 99.9999% of light speed gain mass, exactly as Einstein predicted, and reaching 100% remains impossible. But the Alcubierre solution sidesteps this entirely. The proton equivalent here never accelerates. It sits inside a moving bubble of spacetime. Alcubierre had found a legal loophole in the structure of reality itself. Physicists reading the paper experienced a strange mixture of awe and discomfort. The mathematics was rigorous. The solution was valid. Einstein's equations genuinely permitted this geometry. It felt like discovering that the rules of the universe contain a hidden clause no one had noticed for 80 years. Alcubierre himself was cautious. He presented the work as a mathematical curiosity, not a blueprint for engineering. He knew something was wrong. The equations allowed it, but reality would demand payment. When NASA read the paper, they ran the calculations, and then they went silent. The problem emerged immediately. Creating the Alcubierre geometry required something that should not exist. Negative energy, not antimatter, not dark matter. Negative energy density, energy that behaves opposite to everything we observe. Instead of pulling space-time inward like normal mass, negative energy pushes it outward. It creates repulsive gravity. In nature, every known form of matter and energy is positive. Planets attract, stars attract, gravity pulls things together. The universe has never revealed anything that naturally pushes space-time away. Alcubierre's original calculation in 1994 was devastating. To create a warp bubble 100 meters in diameter would require negative energy equivalent to the mass of Jupiter converted entirely into this exotic form. Jupiter weighs 318 times more than Earth. The energy demand was not merely large, it was absurd. For perspective, all the electrical energy humanity produces in 1 year equals roughly 1 second of sunlight hitting Earth. The Alcubierre drive required energy scales that dwarfed anything imaginable. NASA's conclusion was blunt, mathematically correct, physically absurd. But then in 1997, something unexpected happened. The Casimir effect was measured in a laboratory. Place two uncharged metal plates extremely close together, nanometers apart. Quantum field fluctuations between the plates become restricted. Certain wavelengths cannot fit in the narrow gap. Outside the plates, all wavelengths exist freely. This creates an imbalance. The space between the plates contains less energy than the surrounding vacuum. Relative to the environment, it behaves as a region of negative energy density, and it produces a measurable force pushing the plates together. The force is tiny, comparable to the weight of an ant, but it is real. Negative energy exists, not as some wild speculation, not as a mathematical trick. It exists confined to microscopic scales, under precise conditions, but it exists. This changed the conversation fundamentally. The question was no longer whether negative energy was possible. The question became whether such effects could be amplified, sustained, and scaled up from nanometers to meters. The immediate answer was discouraging. Casimir forces drop off rapidly as separation increases. Scaling them to macroscopic sizes would require precision and stability far beyond current engineering capabilities. The energy demands remained enormous, but the door was no longer locked. In science, moving from completely impossible to extremely difficult represents enormous progress. Impossible means the universe forbids it. Difficult means we simply do not know how yet. The Alcubierre drive had crossed that threshold. It was no longer fantasy. It was a problem waiting for better solutions. And over the next 20 years, the horrifying numbers began to shrink. In 2012, Harold White at NASA revisited Alcubierre's original design with a practical mindset. Alcubierre had optimized for mathematical elegance, not efficiency. His bubble was spherical, with thick walls and abrupt space-time transitions, because those shapes were easier to describe analytically. White asked a different question: what if we change the geometry? He redesigned the bubble from a sphere into a toroid, a donut shape with the ship embedded in the ring. The space-time gradients became smoother, the transitions less abrupt. The result was staggering. Energy requirements dropped from the mass of Jupiter to the mass of Voyager 1, roughly 700 kilograms, a reduction of 1 trillion times simply by reshaping the geometry. Still far beyond current capabilities, but no longer cosmically absurd. The problem had moved from requires planetary resources to requires technology we do not yet possess. That distinction matters. In 2021, new research explored oscillating warp bubbles instead of static ones. Rather than a fixed geometry, the bubble pulses behaving more like a wave than a solid structure. Energy requirements dropped by another factor of 1,000. The latest calculations suggest a warp drive might require energy equivalent to 1 year's output from a nuclear power plant. Enormous, yes, but not stupid beyond measure, not fundamentally impossible. Finite energy requirements, no matter how large, are engineering problems. Infinite requirements are physics saying no. The Alcubierre drive had definitively moved into the first category. Then in 2021, researchers at a DARPA-affiliated laboratory reported something extraordinary. Using dynamic Casimir structures, they created a microscopic warp bubble. Not propulsion, not movement, just geometry. The space-time distortion measured was nanometers across, fleeting and far too weak to move anything. But the shape was correct. The metric matched Alcubierre's predictions. For the first time, the warp geometry existed in physical reality, not just on paper. The effect was tiny. Scaling it up to meter-sized bubbles capable of carrying spacecraft remains a staggering challenge, possibly requiring centuries of development. But existence at any scale matters. Physics does not require practicality to acknowledge validity. If a phenomenon occurs, once it belongs to the universe's allowed behaviors. From there, the challenge becomes growth, rather than permission. The trajectory felt familiar. The Wright brothers flew for 12 seconds in 1903. 66 years later, humans walked on the moon. First prove the concept exists, then scale it, then optimize it, then deploy it. Warp drives had entered that pipeline. But there was a problem far more lethal than energy requirements: As physicists refined the warp drive concept, a horrifying realization emerged. A moving warp bubble does not travel through empty space cleanly. It interacts with everything in its path, and when it stops, the accumulated energy is released. As the bubble moves, particles and radiation in front of it cannot escape. Light cosmic rays, stray atoms, all of it gets compressed at the leading edge of the bubble. The faster the bubble moves, the more severe the compression becomes. Normal photons blue shift into X-rays. X-rays compress into gamma rays. The warp bubble becomes a cosmic snowplow, gathering lethal radiation as it travels. The numbers are catastrophic. A warp bubble traveling at 10 times light speed for 1 year accumulates enough energy that when the bubble collapses and the ship decelerates, the stored radiation is released in a directed beam. The destruction radius extends over 1,000 kilometers. Imagine the scenario. A ship departs Earth, travels to Alpha Centauri at warp speed, and arrives safely. The crew prepares to explore. They shut down the warp drive. The accumulated gamma radiation, compressed and intensified over years of travel, explodes forward in a cone. The beam strikes the star system with the energy of a miniature supernova. Any planets in the path are sterilized instantly. Atmospheres vaporize. Oceans boil away. Continental crust melts. If intelligent life existed in that system, it is extinguished before anyone realizes the ship has arrived. This is not a weapon by design. It is a side effect of geometry, like discovering submarines and then realizing they can carry nuclear torpedoes. The technology itself is neutral. The consequences are not. There is another problem. Warp bubbles are inherently unstable. Any small asymmetry in the energy distribution causes imbalance. The bubble geometry depends on maintaining precise negative energy density in exact configurations. If the symmetry breaks, the bubble collapses. When it collapses, all the stored energy releases at once, not gradually, instantaneously. The ship is vaporized. The surrounding space is flooded with radiation equivalent to a thermonuclear detonation. A warp drive failure does not strand the crew in space. It annihilates them and everything nearby. At this point, the conversation shifted. This was no longer merely a spacecraft. It was a mobile weapon of unimaginable power. Any civilization that developed warp technology would possess intentionally or not the ability to sterilize star systems. The ethical implications are staggering. Does a species capable of warping space-time have the maturity to avoid using it destructively? History offers little reassurance. Every transformative technology, from metallurgy to nuclear fission, has been weaponized. Control over distance is control over access. Control over access intersects inevitably with power, and power in human hands has rarely remained benign for long. You arrive at a distant star system. You announce peaceful intentions, but the inhabitants see a vessel capable of erasing their entire world with a single misstep. How do they respond? They might view your arrival not as first contact, but as an existential threat. Your greeting becomes indistinguishable from an attack. They fire first, not out of hostility, but out of survival instinct. The warp drive does not just enable exploration, it weaponizes space-time itself. And if warp drives exist, if any civilization has ever built one the universe would remember, a warp bubble moving through space does more than transport a ship. It distorts space-time continuously as it travels, and spacetime, when disturbed, responds by radiating gravitational waves. These waves are not like the ones produced by colliding black holes or merging neutron stars. Those events generate brief, violent bursts. A warp bubble, by contrast, produces a persistent, directional signal. The signature is unique, like the sound of different engines: a diesel truck, a jet turbine, an electric motor. Each produces distinct acoustic patterns. Gravitational waves carry information about the systems that generate them. A warp drive would leave a fingerprint unlike any natural astrophysical source. Right now, LIGO and Virgo are listening. These detectors measure space-time distortions smaller than a proton's width. They have confirmed dozens of black hole mergers, neutron star collisions, and other cosmic events. But they are also capable of detecting engineered signals. If any civilization anywhere in our galactic neighborhood has used warp drive technology even once, even 1,000,000 years ago, the gravitational waves from that event are still propagating outward. They travel at light speed, carrying information across vast distances indefinitely. We could detect them. In 2025, the LISA space-based observatory is scheduled for launch. LISA will be 1,000 times more sensitive than LIGO, particularly at lower frequencies where some warp drive signatures are predicted to appear. If an advanced civilization used space-time manipulation technology anywhere within 1 billion light years, LISA might detect it. A confirmed detection would answer two profound questions immediately. First, we are not alone. Intelligent life exists elsewhere in the universe. Second, faster than light travel is achievable, not speculative, not theoretical, proven by the existence of a signal that cannot be explained any other way. The implications extend further. Gravitational wave signals encode information about the systems that produce them. By analyzing a warp drive signature, physicists could infer bubble geometry, energy distribution, and propulsion dynamics. It would be reverse engineering at cosmic distances, extracting design principles from space-time itself. Humanity has often learned by observing before building. We understood stellar fusion long before constructing reactors. We mapped planetary orbits centuries before launching spacecraft. Observation guides engineering. The universe becomes our laboratory. Every major event leaves an imprint in spacetime, and those imprints propagate outward indefinitely. Somewhere within that vast archive may lie evidence of technologies far beyond our own. Instead of asking, "Where are the aliens?" we now ask, "What traces did their ships leave behind?" We have moved from building the ship ourselves to waiting for the universe to send us the blueprint. The search is not passive. It is systematic, rigorous, and expanding. As detector sensitivity improves, the observable volume increases. More potential signals, more chances of discovery. Silence would also be informative. If increasingly sensitive instruments find nothing it suggests, warp travel is extraordinarily rare, constrained by deeper principles we do not yet understand, or perhaps deliberately concealed. But if we do find a signal, it will not arrive dramatically. It will appear quietly in data buried among noise until its meaning becomes undeniable. At that point, faster than light travel stops being a distant ambition. It becomes something the universe has already proven possible. But if we succeed in building it ourselves, the consequences extend far beyond technology. If warp drives become real distance stops, being a barrier and starts being a choice. Alpha Centauri, the nearest star system, currently sits 75,000 years away by conventional propulsion. With a warp drive traveling at 10 times light speed, the journey takes 1 month. Not a generational voyage, not a civilization-spanning ordeal. 1 month. Roughly the time it takes to drive across a continent multiple times or sail across an ocean in the age before flight. A star 100 light-years distant drops from never reachable to 1 year of travel. The Milky Way, our galaxy, stretching 100,000 light-years across, becomes traversable in a single human lifetime. 100 years from departure to arrival at the far edge. The transformation mirrors what happened when humanity moved from sailing ships to aircraft. Crossing the Atlantic once required 6 months by sail with storms, scurvy, and uncertainty. Now it takes 6 hours by plane. You leave after breakfast and arrive for dinner. Distance collapsed from something that shaped entire lives into something measured in a workday. Warp drives would do the same for interstellar space. Science changes fundamentally. Today, astronomy is inference. We analyze light spectra, measure gravitational effects, and build models based on photons that left distant objects millions of years ago. Our knowledge is indirect, always incomplete, frozen in time. With warp capability, inference becomes presence. Instead of guessing at exoplanet atmospheric composition, we send probes to collect samples and return within years. Instead of modeling alien geology from reflected starlight, we land instruments directly on the surface. Entire branches of science shift from remote observation to hands-on experimentation. The feedback loop compresses dramatically. A mission launches, gathers data, encounters unexpected phenomena, and returns with results while the same generation of scientists who sent it is still active. Theories can be tested, refined, and retested within individual careers instead of spanning centuries. Knowledge moves with intention rather than crawling at light speed. Colonization enters an entirely new category. Today, even Mars represents a monumental challenge that stretches resources, psychology, and logistics to breaking points. Worlds orbiting other stars exist only in speculative fiction, too distant for serious planning. Warp drives make them conceivable. We have already identified hundreds of potentially habitable exoplanets, Earth-sized worlds in their stars' habitable zones where liquid water could exist. With warp technology reaching them becomes possible within a single generation. Not easy, not simple, but possible. Humanity transitions from a single planet species to a multi-planet civilization. This shift matters profoundly. A species confined to one world is fragile. Asteroid impacts, supervolcano eruptions, nuclear war, climate collapse, pandemics. Any of these could erase us entirely. Distributed across multiple star systems, extinction becomes extraordinarily difficult. Local disasters remain catastrophic, but no longer existential. If one world fails, others survive. If one branch of humanity faces collapse, others continue. Resilience becomes structural rather than hopeful. The psychological impact is equally profound. For all of human history, the night sky has been unreachable. Stars were distant, abstract points of light, symbols and myths, not destinations. We could observe, but never visit, dream, but never arrive. Warp drives transform the sky from backdrop into territory. Those points of light become places, locations with coordinates, conditions and characteristics, the universe shifts from something we admire to something we navigate. But power at this scale does not arrive without consequences. The same technology that dissolves distance also concentrates immense destructive potential in the hands of whoever possesses it. Control over space-time manipulation means control over who can go where, how quickly, and with what cargo. History offers uncomfortable lessons. Gunpowder nuclear energy, artificial intelligence, every transformative technology has been weaponized. The dual-use nature is not incidental. It is inherent. Warp drives are no different. A civilization capable of warping space-time can explore and cooperate, but it can also strike across interstellar distances with weapons that arrive before any warning is possible. It can deploy forces faster than defenses can coordinate. It can isolate or blockade star systems at will. And as we saw earlier, the warp drive itself is already a weapon. The gamma ray burst released upon deceleration could sterilize worlds. Bubble instability could devastate regions of space. Even peaceful use carries catastrophic risks. This is not speculation about misuse. This is physics describing consequences built into the geometry itself. The question becomes not whether warp drives enable harm, but whether any species mature enough to develop them is also wise enough to restrain their use. And on that question, our own history provides little reassurance. Warp drive technology introduces 3 categories of danger, each severe, each unavoidable. The first is weaponization. Even if the warp drive is not used as a direct weapon, it enables the rapid transport of weapons across interstellar distances. A civilization with warp capability can position forces anywhere in the galaxy within years or decades. No defense has time to prepare. No warning system operates faster than the attacking force itself. Alternatively, the drive itself becomes the weapon. As established earlier, a decelerating warp bubble releases accumulated gamma radiation in a directed cone capable of destroying everything within a 1,000-kilometer radius. Whether intentional or accidental, the effect is the same. A warp-capable ship becomes a tool for annihilating worlds. Whoever controls space controls power, and power throughout history has rarely remained benign. Gunpowder transformed warfare. Nuclear weapons reshaped geopolitics. Artificial intelligence is already raising existential questions about control and alignment. Warp drives would be the most powerful tool humanity has ever touched, and power amplifies intention. It does not create wisdom. It does not guarantee restraint. It simply makes consequences larger and faster. The second danger is cumulative damage to spacetime itself. We do not yet know whether spacetime has limits. A single warp bubble might be harmless. But what happens when thousands or millions of ships continuously warp space across the galaxy? Think of drilling for oil. A few wells cause minimal environmental disruption. 1,000,000 wells over decades create systemic damage that takes centuries to heal, if it heals at all. Ecosystems collapse under sustained stress even when individual disturbances seem small. Space-time might behave similarly. Each warp event creates a temporary distortion. But if distortions accumulate faster than space-time can relax, the effects could compound. Persistent scars in the metric, regions where geometry becomes unstable, cascading failures that propagate across vast volumes. Recent research in 2023 suggests warp bubbles may indeed leave long-lasting imprints in space-time structure. The distortions do not simply vanish when the bubble collapses. They linger, potentially interacting with future warp events in unpredictable ways. We have no idea what the carrying capacity of space-time is. No models predict when widespread warp usage transitions from safe to catastrophic. No experiments can test this at scale. We would only discover the threshold by crossing it, and by then, the damage might be irreversible. The third danger is psychological and cultural. Humans evolved with a deep connection to place. Home is not abstract. It is specific. A landscape, a community, a set of relationships embedded in physical proximity. Our sense of identity, belonging, and meaning is tied to where we are. Warp drives sever that connection. If traveling between stars becomes as routine as flying between continents, what does home mean? If you can reach a dozen different worlds within a lifetime, which one defines you? Cultures that develop on different planets under different stars will diverge. Different gravity, different day-night cycles, different ecosystems. Over generations, these differences compound. Language shifts, values evolve. What it means to be human begins to blur. We have not yet solved conflicts within a single species on a single planet. Extending that species across 1,000 worlds with independent development and divergent interests seems unlikely to reduce tension. More likely, it magnifies existing problems while introducing new ones we cannot yet imagine. The story has shifted. The question is no longer, can we do this? The question has become, should we? But perhaps the largest question is not what we will do. Perhaps it is whether we are even the first to face this choice. If warp drives are physically possible, why don't we see anyone using them? The Fermi paradox takes on new urgency in the context of faster-than-light travel. The universe is 13.8 billion years old. Our galaxy is 100,000 light-years across. With warp drives traveling at 10 times light speed, a single civilization could colonize the entire Milky Way in just 10,000 years. 10,000 years is nothing on cosmic timescales. A rounding error, a brief moment. If any civilization anywhere in the galaxy developed warp technology even 1 million years ago, they should be everywhere by now. Every star system, every habitable planet, every resource-rich asteroid belt. The galaxy should be full of their presence, their infrastructure, their signals. Yet we see nothing. It resembles the illusion of an empty Europe before Columbus arrived. Europeans believed the Americas were uninhabited wilderness. In reality, millions of indigenous people had lived there for tens of thousands of years. The emptiness was not real. It was a failure of observation and recognition. Perhaps we are making the same mistake. Perhaps the signatures of advanced civilizations surround us and we simply lack the tools or understanding to recognize them. Gravitational wave patterns we dismiss as noise. Megastructures we misinterpret as natural phenomena. Technologies so far beyond our comprehension that we mistake them for physics. Or perhaps we truly are alone. 3 possibilities emerge, each unsettling in different ways. First, we are the first. In the entire history of the Milky Way across billions of stars and trillions of planets, we are the first species to reach this threshold. Statistically unlikely, but not impossible. Someone has to be first. Perhaps it is us. Second warp drives encounter an invisible barrier. Some deeper physical principle we have not yet discovered prevents sustained space-time manipulation at the scales required for interstellar travel. The mathematics allows it, but reality imposes constraints the equations do not capture. Every civilization reaches the same point we have and then finds the door locked by physics we do not yet understand. Third, advanced civilizations exist but remain hidden. Either they have detected us and chosen not to make contact, or they operate in ways we cannot perceive. Perhaps they learned that broadcasting one's presence invites danger. Perhaps warp drive signatures are deliberately suppressed. Perhaps they exist in forms or dimensions our instruments cannot access. There is a fourth possibility, darker than the others. The Great Filter hypothesis suggests that something prevents most or all civilizations from advancing beyond a certain point. Self-destruction through war, environmental collapse, or technological misuse. Or perhaps the warp drive itself is the filter. Any species that learns to manipulate spacetime gains the power to destroy itself and others. Most fail the test. They build the drive, use it recklessly, and trigger catastrophic consequences. Spacetime scars accumulate, warp bubble instabilities cascade, weapons proliferate faster than wisdom. Only civilizations mature enough to develop warp technology and restrain its use survive. The filter is not technological, it is ethical. If this is true, then warp drives are not merely an engineering challenge. They are a test, a threshold that separates species capable of long-term survival from those destined for extinction. The universe hands us the key and waits to see what we do with it. As of 2024, we do not have warp drives. But for the first time in history, they are not impossible. They have moved from fantasy into the category of engineering challenges. Difficult, perhaps, requiring centuries of development, but no longer forbidden by the laws of physics. We do not know if it will take 100 years, 1,000 years, or whether we will ever succeed. But the mere possibility changes everything. It transforms how we see the night sky. Those distant points of light are no longer unreachable. They are simply far, and distance, as we have learned, can be bent. The ending is not written, because the ending is ours to create.